the lecture today is proof term and Curry-Howard isomorphism. Curry-Howard isomorphism. The basic idea behind the Curry-Howard isomorphism is, given a proof deducing truth statement A true, so we have a proof D deducing truth statement A true, we can represent this proof D using a program called M of type A. So this is a program and this is a type. So proof is represented as program, and this proposition A now is interpreted as a type. So we see two kinds of correspondences. The first is propositions as types correspondence. That is, propositions in logic. So this is logic. Propositions in logic, they are actually the same notion as types in programming languages. The second is proofs as programs correspondence. So in logic, we have this proof, and this proof will be represented as program in this programming language. In our case, we will call this program as proof term. So proofs in logic are actually programs in programming languages. That's the Curry-Howard isomorphism. Now, given a system of logic, so we have this system of logic, we apply Curry-Howard isomorphism, and then we can derive in a mechanical way a corresponding programming language with programs, syntax of programs, and types. And the set of propositions in logic is identical to the set of types in this programming language. That's the Curry-Howard isomorphism. Now, let's apply this Curry-Howard isomorphism to the system of logic we have developed so far, which is net propositional logic formulated in natural deduction style. So we have propositional logic formulated in natural deduction style, and we are going to apply Curry-Howard isomorphism to this logic, and then we will obtain some programming language. And we can derive this programming language in a systematic way, and here is how. So in our system of inference rules, this propositional logic, we have many inference rules, right? So suppose that we have an inference rule of this form, say A true. So this inference rule R deduces A true. So for example, here A can be A1 conjunction A2, or A can be A1 implies A2, etc. And now we have this premise, and let's say the proof is D. And we will derive a corresponding rule in this programming language. And the idea is that we represent the whole proof D here using program M. So in other words, the derivation tree or the proof in the premise will be represented as a single program, and we will call this is proof term. So the whole derivation tree, the whole proof is now represented as a single proof term. And this proof term will be assigned the same type A. So proposition in this logic, this is a proposition, is now used as a type. And then by convention, we assign the same name to this inference rule. And we repeatedly apply this transformation to the premise of this inference rule. So now we have another system of inference rules using natural deduction. So that's the basic idea. So we already have the syntax for these propositions. So the syntax for types is fixed. And we decided to use the same name for this inference rule. So the names for inference rules are already fixed. Now the remaining question is, what is the syntax for these proof terms? It turns out that we may choose any syntax for these proof terms as far as this proof term essentially captures everything in the proof in the premise. So in other words, as far as this proof D is shown to be equivalent to proof term M. So proof term M captures everything in this proof D, then we may use any syntax. But we will use the syntax for simply typed lambda calculus. Simply typed lambda calculus. Because that's the origin of this simply typed lambda calculus. So remember that we may use any syntax for proof terms, but we will use the syntax for simply typed lambda calculus. So we can systematically derive these inference rules for this simply typed lambda calculus from the inference rules for proposition logic. Okay, that's how Curry-Holder isomorphism is going to work on proposition logic. So let's derive these inference rules by considering each logical connective individually. The first is logical conjunction. So we have this introduction rule, conjunction introduction rule, A true, B true, and this is the conjunction introduction rule. What kind of inference rule can we automatically derive mechanically? So suppose that the proof of A true is DA, and the proof of truth judgment B true is, let's say, DB. So we have to reason inductively. Suppose that according to the Curry-Holder isomorphism, this proof in the premise is represented as proof term M of type A. This proof term M is going to have the same type A shown over here, according to the Curry-Holder isomorphism. And similarly, let's assume that this proof is represented as a single proof term M of type B. According to the principle, this proof term M must have a type B, the same type B shown over here. Then, now the whole derivation tree or the whole proof can be represented as so we will assign the same name for this typing rule, conjunction introduction rule. And so whatever comes here, this is going to be new proof term, should be should be expressive enough to represent everything shown over here, which is this one. So in other words, this derivation tree, so these proofs were converted to these two proof terms. And this proof term should contain everything shown in the premise. So we choose to use this form of syntax m, n. This is actually called product term from the lambda calculus, and we assign type A conjunction B. So again, you may choose any syntax for this proof term. So for example, if you like, you may use some new form of proof term, for example, m#n. But this is fine because you do not lose anything. It still conveys everything in the premise m and n. But we'd like to reuse the syntax from the simply typed lambda calculus. So we use this proof term, product term. So we have just derived a corresponding inference rule here. What about conjunction elimination rule? We have suppose that we have A conjunction be true. By applying conjunction elimination rule left, we can deduce A true here. Now suppose that the whole proof in the premise is D. Then apply the Curry-Horde isomorphism to the premise, and we obtain a proof term M of type A conjunction B. Then we use the same inference, the same name for the inference rule, and then the new proof term here will have a type A. And again, we may choose any syntax for this new proof term, but we'd like to reuse the syntax for simply typed lambda calculus. So we'd like to use this projection term. So this is called projection term. And the symmetry case is conjunction elimination right rule. We have A conjunction B true. By applying this conjunction elimination right rule, we have B true. And according to the Curry-Horde isomorphism, let's assume that the premise is represented as a proof term of type A conjunction B. And we apply the same inference rule, conjunction eliminate right, and then it's going to have type B. So we carry this type over here. And again, any syntax is fine for this new form of proof term, but we'd like to use the projection term. So we use the second M. So we have systematically derived these new inference rules from the inference rules for logical conjunction in propositional logic. And similarly to the propositional logic here, we formulated the new inference rules in the natural reduction style because we have this introduction rule. Because if we read this rule top down, you introduce this one, and we also have a corresponding elimination rules. So this is the first example of applying Curry-Horde isomorphism to derive these inference rules. So this judgment is actually called typing judgment. Well, this is the truth judgment, and this typing judgment, because essentially it says this proof term has this type. Now let's look at implication. So in propositional logic, we have this implication introduction rule. Implication introduction rule. A implies B true. We introduce a hypothesis, A true, and then it deduces B true. And then we label this hypothesis with, say, label X. Now let's apply Curry-Hall isomorphism to derive a corresponding typing rule. I mean the inference rule for typing judgment. First, we have to think inductively. So suppose that the proof in the hypothesis, the proof in the premise is called B. And we apply Curry-Hall isomorphism to disprove D and obtain some new proof term. Let's say it is M. Is M of type B. So, but what about how do we translate this hypothesis? So this hypothesis is going to have type A because this proposition is going to be interpreted as type. And it is also hypothesis. But what is the proof term that we should use here? If you think about the meaning of this hypothesis, it means that we don't know the actual proof of this A true. We just assume that there is a proof. So the proof is actually unknown here. We just assume that there is a proof of A true. Similarly here, we don't know the actual proof term that should have a type A. It's just unknown. Because we do not know the actual proof term of type A here, we use a variable. And we reuse the label for this hypothesis as the variable here. So we translate this hypothesis to this hypothesis assigning type A to this proof term variable. Now we have finished translating the premise where we use this variable. And then now the whole proof will be represented as a proof term here. And it's going to have a type A implies B, and we use the same name, implication introduction rule. And any syntax is fine for the proof term here, as far as it captures everything. But we decided to use the syntax from simply typed lambda calculus. So, for example, you may choose to use a new form of a syntax, a new form proof term, say we need X, and we need A, and we need M. So we can use this triple. But instead of this funny syntax, we'd like to use this lambda abstraction. Lambda, X has a type A, and its body is M. So this is where the lambda abstraction actually originates from. So we have finished translating the inference rule, implication introduction rule in logic into an inference rule for typing judgment in this new programming language. One thing that you should notice here is, remember that in this hypothetical proof, you may use this variable, you may use this hypothesis 0 times, only once, twice, or actually as many times as you like. It's okay because that's what propositional logic allows. And similarly, you may use this variable inside proof term M here 0 times, 1 time, twice, or as many times as you like. So for example, we might have something like lambda x a dot x comma x. which corresponds to a hypothetical proof here, where the hypothesis is used twice. If this hypothesis is used twice, then we will see 2 copies of variable x in the corresponding proof term. Or you may choose not to use this variable x at all. But for example, you may choose not to use this hypothesis. And similarly to the scope of this hypothesis, we have the same notion of a scope. So suppose that, so let me write again here. A true, B true, and this is the label x. And we learned that the scope of this hypothesis is limited to the premise of this inference rule. You may not use this hypothesis outside this inference rule. So for example, outside here. It is not supposed to escape from the premise of this inference rule. This is not legal. Similarly here, we have the notion of scope. This variable had the scope limited to this premise, or equivalently, this proof term. In other words, you may use this variable x inside this proof term m, just like this hypothesis should be used only inside this hypothetical proof. And you may not use this variable x outside. So for example, lambda x dot, well, this is fine because this variable x is used inside this the body of this lambda abstraction, but this would be wrong because this x is not found in the body of this lambda abstraction, just like your intuition tells. So what we have seen so far is we were able to translate this inference rule into a corresponding inference rule for typing judgment, introducing a new form of proof term, which is called lambda abstraction. And we have also seen that the same phenomenon occurs. Here, this hypothesis is limited to this premise. Similarly, this variable, its scope is limited to this proof term m. And we may use this hypothesis as many times as you like. And similarly here, you may use the same variable, this variable x, as many times as you like inside this proof term m. So essentially, there's no difference. And that's not surprising because according to Curry-Howard isomorphism, this logic is no different at all from this programming language. So there's no difference. If you see some particular phenomenon here, you are going to see precisely the same phenomenon in this programming language. So now let's look at the implication elimination rule. So let's say A implies B true. We apply implication elimination rule, and we have to have another proof of A true, and then you use B true. So let's apply. Again, we have to think inductively. Our goal is to translate the whole derivation tree, and we are going to think inductively. So we look at the smaller ones first. Let's say this has a proof D of D1. Let's say this has proof D2. Or let's say just D and E, calligraphy E. And according to the isomorphism, let's just say the first inner derivation tree, this proof has been translated to M of type A implies B. And the second proof has been translated to another proof term N of type A. And the question now is, what is the new proof term which must have a type B? Okay, and we assign the same name. And again, you may choose any syntax for this new proof term, but we'd like to use the so-called lambda application. So it's going to be just the M juxtaposed with N. So we have finished translating these inference rules. Again, there's no difference at all. So we have implication introduction, implication elimination rule. And here we have implication introduction and implication elimination rule. The next exercise is about disjunction. Okay. Disjunction. So in the system of in the proportional logic, we have this disjunction introduction rule. If you have A true, you can deduce A disjunction B true. And this is disjunction introduction rule. And let's translate this inference rule to another inference rule of the same name. So we think inductively, and this proof D has been converted to proof term M of type A. And now this new proof term will have type A disjunction B, and with the syntax injection term, injection left, injection term, or in left. So we have injection left with M. But a slight problem here is by analyzing this proof term M, we can eventually deduce its type. So A is not missing, but there's no way to extract B from in left M. B is gone for good. So in order to recover the second component B, we annotate this injection left with B. Now we can reconstruct the whole type A disjunction B. A from essentially M, A essentially from M, and B from this annotation. And we have symmetric case for this is a disjunction introduction rule left, and we also have disjunction introduction right case. What about elimination rule? So this is the elimination rule for disjunction. So we have to consider two branches. The first assumes A true and then deduces C true. And the second branch assumes B true and then deduces C true. Then whichever branch you take, you can eventually prove C. So now you can deduce C true. This is the disjunction elimination rule. Because we introduce hypotheses here, we have to label them. So we use label X and Y. X and Y. And similarly to the case of lambda abstraction, the scope of this hypothesis is limited to this proof, and the scope of this hypothesis is limited to here. Now let's translate this inference rule. Okay, suppose that this proof D, deducing A disjunction B true, has been translated to M of type A disjunction B. Let's say this is proof E. Suppose that E has been translated to, let's say, proof term N, proof term N of type C. But similarly to the case of lambda abstraction, you have to introduce new variable here. So this hypothesis will be translated to this hypothesis of this form. But the question is, what is the proof term here? We don't know because the actual proof of this truth assessment A true is unknown. So this proof term is unknown. So we'd like it to use instead variable. So we use this label for variable X. Okay. And similarly here, suppose that this one has been translated to N prime of type C, starting with label B colon Y colon B. And then this is going to be disjunction elimination rule. And The final proof term is going to have a type C, and you can use any syntax for this proof term, but we'd like to use the case term, the so-called case term. So the syntax goes case m of. So we carry this proof term over here, and then if this is injection left x, then injection x of type A, but actually this would be unnecessary, of n, or if injection right in the right branch, we assume y, and then you get n prime. So this is a new form of proof term called case term, and it's going to have a type C. So in this way, we can translate in a straightforward way the inference rule for disjunction elimination into a corresponding inference rule for typing judgment with the same name. The remaining two cases are about truth judgment and falsehood judgment. Truth, first the top, truth, top. So we have only introduction rule, so top true, and the premise is empty, and this is top introduction rule. So let's translate this inference rule. Because the premise is empty, the premise here should be empty too. And the proof term is going to have type top, and you may use any syntax. And we use this unit term, and this is going to be top introduction rule. And what about bottom? It is falsehood. This is bottom. So bottom true allows us to prove any truth judgment where C can be anything, and this is the bottom elimination rule. Let's try to translate. Suppose that the premise has proof D, and D is translated to M, and it's going to have a type bottom. Now, the resultant in the conclusion is going to have a type C, and the question is, what is the syntax for this proof term? And it's going to be bottom elimination rule. And we use this abort term, abort M. So this is the keyword. And similarly to the but it's impossible to deduce this type C, so we annotated this abort with a C. Now we can always get the type C by looking at the annotation here. So there's a good reason why we call this proof term as abort term using this keyword abort, because later it turns out that this abort really corresponds to a phenomenon where we just aborted the computation. So intuitively, this computation is not supposed to complete returning a value, so we just abort. So things will be clear later when we consider the operation semantics of this language, where it comes from. So for now, let's just say we use this abort to imply that the computation will be aborted later. Now let me summarize the whole story so far. So we have this propositional logic using truth judgment, A true, and we use this proof. And it is formulated in natural deduction style. And what we have just finished is we apply Curry-Horde isomorphism to derive another system of inference rule, which also uses the natural reduction style, but this time we use a typing judgment of this form M:(A). So we see the correspondence between proposition, this is a proposition, and types, and this proof, correspondence between these proofs and programs. So this is a proof term, or the program in this new programming language. So this is typing judgment. So we have formulated a new system based on natural reduction principle for this typing judgment. Now, previously we learned this hypothetical judgment. We actually derived another system using hypothetical judgment. So this time, the judgment is going to have this form: A1 true, AN true, turnstile C true. Remember that this hypothetical judgment of this form has no new semantic implication. It's just the syntactic tool. It's a syntactic tool developed to facilitate the reasoning in this logic. So it allows us to easily keep track of the scope of every hypothesis. So it is just a syntactic tool, and we were able to derive essentially the same system using natural reduction style. Now, what about this way, using hypothetical judgment? Alternatively, what about applying Curry-Hall isomorphism to this system? And it turns out that whichever way we take, we always arrive at the same system. So if we take this path, what that means is that U is a turnstile. On the right side, we have this M:(A), and here we are going to have hypothesis, but in this language, the hypothesis has this form, variable (A). So we have something like x1 has a type A1, xn has a type AN. So starting with this system, you rewrite the system using hypothetical judgment. Then we obtain another system, which is no different semantically, another system using this form of judgment. Or you could apply Curry-Hall isomorphism to this system, which starts with hypothetical judgment. Now we represented the proof, the whole proof, with a proof term M, the whole proof here as a proof term M, and these are hypotheses, so we converted them into hypotheses of this form. So it turns out that either you can take this path or this path, but always you end up with the same system, which uses the familiar typing judgment for this language. And the proof terms are from simply typed lambda calculus. So now we have inference rules for typing judgment of this form. So we have type system. So our journey goes like this. We started with purely logical stuff, propositional logic, formulated in the natural reduction style. And then we applied the Curry-Hall isomorphism, either first applying the Curry-Hall isomorphism and then reformulating using hypothetical judgment, Or alternatively, you could reformulate first using hypothetical judgment and then apply Crayhold isomorphism. Whichever path you take, you always end up with another system of inference rules, which is essentially the type system for simply typed lambda calculus. So what we have learned is this Crayhold isomorphism is a powerful principle connecting a system in logic into a type system, of course syntax, and type system in programming languages. So for example, you could imagine another logic, for example linear logic, and apply Crayhold isomorphism, and then suddenly you obtain linear lambda calculus. And later we will expand this system of logic, for example, to first order logic, or higher order logic, and then apply Crayhold isomorphism, and then you obtain corresponding language. For example, higher logic corresponds to polymorphic lambda calculus, and so on. So the principle is really simple, but that's the beauty of the study of programming language theory. So we started in logic. Now we are looking at type theory. So the Crayhold isomorphism is the principle that underlies both logic, the connection between logic and type theory.